sun is our nearest star. The only star we can see is more than just a point of light. How do we learn about the sun? At solar observatories, astronomers direct their mirrors at the sun. They catch its light and send it into their laboratories for study. The angular diameter of the sun can be measured. When that information is combined with the sun's mean distance, astronomers can calculate its linear diameter, approximately 864,000 miles. By calculating its surface area and measuring the amount of energy it gives off, the surface temperature of the sun can be found. About 5,800 degrees Kelvin, or about 10,000 degrees Fahrenheit. How does our sun compare with other stars? This is a diagram which plots the brightness of a star, with the sun as a standard, against a star's color, which is a measure of its temperature. The color ranges from the hottest type O stars, which are blue, through the various colors to the coolest type M stars, which are red. The vertical scale shows brightness in terms of the sun, from 1/1,000,000th the sun's brightness to 1,000,000 times the sun's brightness. This kind of diagram, which is called a Hertzsprung-Russell or HR diagram for the two astronomers who developed it independently, sets the sun as the standard of brightness. The sun is a yellow star, spectral type G. Astronomers found that nearly all stars plotted on an HR diagram lie within this narrow band called the main sequence. In main sequence stars, there is a definite relationship between surface temperature and brightness, as well as between size and mass. Sirius, the brightest star to the naked eye, is a main sequence star. Sirius is hotter than the sun and brighter. It is also larger, with about 1 1/2 times the sun's diameter. This chart doesn't show relative distances between stars. It simply compares temperature and brightness. Wolf 359 at the bottom of the main sequence is cooler than the sun and dimmer. It is a small red star, about half the temperature and diameter of the sun. Most stars seem to be red dwarfs, like Wolf 359. But not all stars are main sequence stars. One such star that is not on the main sequence is Sirius B, a white dwarf. Most white dwarfs are hotter than the sun, but since their total energy output is much less than the sun's, their size must be very small, even smaller than the Earth. But up here on the HR diagram, in the region of the giants, we find yellow stars like Capella and red stars like Arcturus. They're not on the main sequence because they give off more light than their temperatures indicate they should. This discrepancy is a clue to their large size. We can't show the supergiant Betelgeuse to scale on this chart. It's more than 2,000 times larger than the sun in diameter. To this scale, with the sun a disk 2 inches in diameter, Betelgeuse would be far larger than the entire chart. To the same scale as the 2-inch sun, Betelgeuse is more than 350 feet in diameter. But even with its great size, Betelgeuse has only about 10 times the mass of the sun. Most stars, astronomers have observed, have masses between 1/10 and 5 times that of our sun. Compared with most of these stars, our sun is a giant. So there are differences in size and mass, brightness and temperature of stars. What about composition, the materials a star is made of? Clues to the sun's composition come from its spectrum. When the light of the sun is passed into a spectrograph, the familiar pattern can be studied. Spectra of the sun and stars are usually not photographed in color because it's the black lines that give astronomers the information they're after. The lines are clues to the chemical elements in stars. Probably all of the elements that occur naturally on Earth are present in our sun, although only about 70% of them have been identified so far. At the surface of the sun, about 90% of the atoms are hydrogen, and almost all the rest are helium. Only a very small proportion are of the heavier elements. When the light from other stars is analyzed, their spectra reveal that the composition of most of them is about the same. Hydrogen and helium are the two main constituents of all stars. The stars, like our sun, are great spheres of gas at very high temperature. What else do we know about the sun? We know that the sun rotates. By following the movement of surface features, like sunspots, astronomers have determined the sun's speed of rotation. Because the sun is not a solid, but a gas, actually in the plasma state, different parts of it rotate at different speeds. At the equator, the period of rotation is 25 days. Here, the period of rotation is fastest. Halfway to the poles, the period is nearly 28 days. And at the poles, periods of more than 30 days have been reported. The sun's period of rotation can also be measured by means of spectroscopic studies of its light. Spectra of other stars indicate that they probably rotate much as the sun does. The light and other radiation of the stars, which give us all our information about them, are the result of a tremendous outpouring of energy. The energy comes from nuclear processes that mainly take place deep within the core of the star. At temperatures perhaps as high as 25 million degrees Fahrenheit, hydrogen atoms are changed into helium atoms by the process we call fusion. We can explain the fusion reaction in a simplified way like this. We begin with two protons. Each one is the nucleus of a hydrogen atom. The protons fuse and produce a hydrogen-2 nucleus, heavy hydrogen, or deuterium. A positron is given off. When the positron is annihilated by an electron, energy is the result in the form of gamma rays. When the H2 nucleus collides with another proton, a nucleus of helium-3 is formed, and there is another burst of radiant energy. These are also gamma rays. When two helium-3 nuclei collide, they produce a nucleus of helium-4. This releases two protons, and the cycle can start again. It's called the proton-proton cycle. In the process, mass is converted to energy. The proton-proton cycle produces energy in stars whose masses are about the same as the sun, or less. In more massive stars, a carbon-nitrogen cycle occurs. A carbon-12 nucleus absorbs a proton and changes to a nucleus of nitrogen-13. Gamma rays are given off. The nitrogen-13 is unstable and changes to carbon-13. Collision with another proton changes it to nitrogen-14 and releases gamma rays. Another proton collision changes it to oxygen-15 with more gamma rays given off. Oxygen-15 is unstable and becomes nitrogen-15. One more proton collision splits the nitrogen-15 nucleus into a helium nucleus and a carbon-12 nucleus. Gamma rays are again given off, and the carbon-nitrogen cycle can begin again. So in all stars, hydrogen is gradually converted to helium with the release of tremendous amounts of energy. The life story of a star is essentially a story of this continuous transmutation of hydrogen to helium. A star like the sun begins as a cloud of hydrogen gas. like the dark Horsehead Nebula in the constellation Orion. As gravitational forces shrink the cloud, potential energy is released in increasing amounts of radiant energy, and the cloud begins to glow, like the great nebula in Orion. Now the interior density and temperature increase until conditions are right for nuclear reactions to begin, and a star is born. These are young stars in the Pleiades group, perhaps less than 100 million years old. The glow around them is probably the remains of the gases from which they were formed. At this time of its life, a young star is on the main sequence, like our sun. It's believed that our sun has been a main sequence star for about 5 billion years. Astronomers estimate that it will take another 5 billion years for most of the hydrogen in its core to be converted to helium. With this change in composition, a star increases in size and brightness and becomes a red giant, only to shrink in the course of millions of years into a white dwarf. In this form, a star dies. Some stars end their lives more spectacularly. The Crab Nebula was formed by an exploding star, a supernova. At its center is a pulsar, a tiny, rapidly rotating, pulsating star believed to be the remains of that cataclysmic event. Astronomers believe the Ring Nebula was formed from an exploding star, a nova or supernova. They think the same might be true of the Dumbbell Nebula and the Veil Nebula. Exploding stars are rarities in the universe. More commonly, a star's life takes it from gas cloud onto the main sequence, then into a red giant, and then to a white dwarf. Our sun is a middle-aged, ordinary star, not much different from billions of other stars in the universe. But it is the only one we can study relatively closely, and the one on which life on Earth depends.